Hello ladies and gentlemen, my name is David Hills, the Scientific Director for Separation Science, and I'd like to welcome you all to our latest webinar in collaboration with supleco. Our topic today is Solid Phase Extraction, Fundamentals and Recent Developments. Before we begin, I'd like to cover some administrative details. If you look toward the bottom of your screen, you'll see a Q&A box, and you can ask questions at any point during the presentation by typing them in the box and clicking the send button. Questions will be answered at the end of the formal presentation, and any questions that we don't cover may be answered offline afterwards. Please note that submitted questions are not seen by the other attendees, so don't be shy about asking them. You'll also notice a full screen button in the upper right portion of your screen. You can press this if you'd like to view a larger version of the presentation. If at any time during the webinar you require technical assistance, you can type in your comments in the Q&A box and the technical team will respond to you directly. This presentation will be recorded and you'll all be sent a link to the recording by email over the next few days. So with that out of the way, let me introduce our presenter for today's webinar. Olga Shimelis is a principal R&D scientist working in the sample preparation group at supleco. She leads a research team in the development of new extraction and analysis methodologies using solid phase extraction, LC-MS and GC-MS, primarily in the areas of food and environmental analysis. Olga has made significant contributions to innovative SPE product lines, which include molecularly imprinted polymers, Z-SEP sorbents for the captures method, and the asset sampler for measuring isocyanates in air. She received her PhD from the University of Oklahoma and joined supleco after completing her postdoctorate work at the Northeastern University's Barnett Institute of Chemical and Biological Analysis in Boston. And so, without further ado, I'll turn the presentation over to Olga Shimelis. Olga?
Yes, thank you, David, for the introduction. And hello, and thank you all for attending this webinar. We are going to talk today about solid phase extraction, about its fundamentals and recent developments in the area. SPE, as it's known, has become the most powerful technique available for rapid and selective sample preparation prior to chromatographic separations. That's because SPE has many advantages. It extends the lifetime of the chromatographic systems and improves qualitative and quantitative analysis. If you look at the time spent on the analytical processes, sample processing still takes the biggest chunk of the time from any lab work. It can present a significant bottleneck. It can account for over 61% of time spent on analysis and can contribute to 30% of the experimental errors. So choosing the correct sample prep protocol can go a long way to making an analysis more reliable and increasing laboratory throughput. Where does solid phase extraction fit in an analytical chromatography workflow? Solid phase extraction is a sample preparation technique. So right after sample collection, you apply solid phase extraction to a wide variety of matrices, and it comes prior to HPLC or GC analysis. SPE is a form of liquid chromatography. The particle size for SPE that's used for SPE is larger than that for HPLC. And SPE can be selective and versatile. Many sorbents and elution conditions are available. What are the goals in using SPE extraction? The first characteristic of a good SPE method is to obtain high analyte recovery, and that contributes to higher sensitivity of the analytical methods. Then is to provide the minimal interference from sample matrix. That contributes to both sensitivity and good resolution. The analyte concentration is one of the goals of the SPE. So that's again is a sensitivity issue, and you can pre-concentrate analyte during the SPE method. the method should be simple and require the minimum amount of steps. That contributes to the speeding up the method when you're performing that in the laboratory. And of course, the method is required to be reproducible, short, and uses minimum wash and elution solvent to be economical. Now we're going to look at how does SPE work. There are two different elution strategies in SPE, and it depends on the goal of the extraction, which strategy one chooses to use. The bind-elute strategy that is shown on the next slide is the more common strategy, where the analytes are bound to the sorbent and then unwanted matrix components are washed off, and then the analytes are eluted. And different elution conditions can elute different analytes, so the fractionation also is possible with this method. The second strategy is interference removal strategy, and that strategy is a pretty quick strategy, whereas the sample passes through the tube and all matrix components are left on the tube or a SPE device, and the analytes are washed off. So let's look for bind-elute strategy in more detail. So the original sample is loaded into the preconditioned SPE tube or cartridge, and the analytes remain bound to the cartridge, whereas the matrix components and unwanted components are washed through using the wash solvent. Then the elution solvent is applied, and the analytes is eluted from the cartridge. Then they're pre-concentrated, and HPLC or GC analysis is done. Another strategy, let me take this one out, is the interference removal strategy. You can call it chemical filtration. Again, the sample is applied to the tube, but in this case, the matrix remains bound to the SPE sorbent, and the analytes just pass through. So, again, the analytes are pre-concentrated prior to the HPLC or GC analysis. Again, for this type of strategy, one needs to take care of what kind of a SPE sorbent to use. So they would remove the matrix component and don't bind the analytes. So on our next slide, we'll look at type of retention mechanism and sorbents that are used in SPE. The first mode for SPE is a reversed phased, and this is the most popular mode in HPLC, so the SPE has it too. It's when the analytes interact with a SPE sorbent using nonpolar hydrophobic interactions. And usually it's applied to aqueous samples such as biological fluid or environmental water samples or aqueous food extracts. The analyte has to be nonpolar or have nonpolar functionalities to bind to the reverse phase SPE supports. Most organic analytes would fall into this category. They would have alkyl aromatic or alicyclic functional groups. And then once they're bound to the analyte, you can disrupt that interaction by using nonpolar solvent mixtures or organic solvents, including methanol, acetonitrile, dichloromethane, or buffer solvent mixtures. The common application for reverse phase SPE would be for biological fluids such as plasma, blood, urine, for water analysis, and for aqueous extracts. The common sorbents that are used in reverse phase SPE can include C18 functionalized silica supports, can include polymeric SPE, and even carbon can function as a reverse phase SPE. The next SPE mode would be normal phase SPE, and these are used for organic extracts or samples extracted into organic solvents. Analytes interact with the SPE supports through polar interactions, and analytes themselves exhibit some kind of polar functionalities through which they can interact. So the polar interactions, hydrogen bonding pi-pi, dipole-dipole interactions are common. Again, it's for nonpolar samples, and the polar interactions are disrupted with a more polar solvent or solution to elute the analytes off. The common application would be organic extracts from environmental samples, fractionation of petroleum hydrocarbons, or you can fractionate fats. And the common sorbents include silica, ONH2 functional silica, fluorosil, and alumina. And then we come to the third mode of SP, which is ion exchange SP. It involves the interaction between charged or dipole groups on the analyte with the positively or negatively charged groups on the SPE phase. So the electrostatic interaction is the main type of interaction mechanism. And this type of SPE is also one of the hardest to understand and to develop metal for because of a lot of equilibria that takes place both with sorbent and with analyte, the acid-base type of equilibria. So also you have to keep in mind that not only electrostatic interactions take place, you can also have some reversed phase interactions, such as in a mixed mode ion exchange SPE. So the sample matrix that you would use would be aqueous or organic, but the analytes should have some kind of ionizable functional groups, so they will be bases or acids. And to elute those analytes of the SPE support in a bind-dilute type of strategy, you would have to disrupt these electrostatic interactions, and they can be disrupted via two ways. One would be the pH modification to neutralize either the compound or the sorbent functional groups, and the second one is to introduce stronger counter-ions to compete for ion exchange binding sites on the sorbents, and we're going to look at this in more detail in the next few slides. However, there's a big advantage of this type of ion exchange SPE is that because of the electrostatic strong interactions, we can use 100% organic washes in this type of SPE, which contribute to the cleaner samples in the end. So what are the useful ion exchange SPE tips? The first one, the ion exchange kinetics is a little slower than reverse phase and normal phase SPE, so one would have to reduce the flow rates when using this SPE, make sure the analytes are properly retained on the cartridge. Then there could be strong versus weak ion exchanges that are available. The strong ion exchanges SPE supports, their functional groups are always ionized regardless of pH. That would include, for instance, quaternary amine groups that are always positive on the SPE sorbent. And then there are weak anion exchanges where sorbent functional groups have controllable pKa and they can be neutralized to elute the analytes off. Another thing to keep in mind is the selectivity for counter-ions of different ion exchange supports. For example, for cation exchanges, interaction with ammonium cations is stronger than with sodium cations or protons. So in practical terms, it means that if the ion exchange arrives from manufacturing the protonated form, that proton can be easily replaced with another counter-ion, such as ammonium. Or in other words, the ion exchange in the protonated form can easily be used to retain the amine-containing analytes. So most manufacturers will tell you what is the final form of the ion exchanger, and you can base your methods on that information. So then this is a very busy slide that explains the role of pH in the retention of analytes on the SPE phase. So understanding this acid-base equilibria is important for properly choosing loading, washing, and elution pH conditions. In this slide, the blue form of analyte promotes hydrophobic interactions, and that's the neutral state of the analytes. And the ionized state is green, and that promotes electrostatic interactions. So both acids or bases, depending on pH, can be present as a neutral or charged states. So when they're in the neutral state, for instance, for the acid, the neutral state would be a protonated state, and that state is possible with pH lower than the acid pKa for at least one pH unit. So 100% HA is present at low pH. So if you lower the pH, then you can load the acid on the reversed phase SP, for instance, because they're neutral. At high pH, the acid is deprotonated and present at the charged state. So that's when the ion exchange SPE can be used to retain the acid. So there are a few things that keep in mind in this slide. For instance, that the presence of halogen atom near carboxy group strengthens acid effects. You need to know the pKa's for most acids to choose the proper loading, elution, and wash conditions for the SPE method, and the same is true for the bases as well. So this next section briefly summarizes what you need to do to develop good SPE methods. First of all, you have to look at your analyte of interest and see which functional groups determine its interaction with SPE sorbents. So you can have hydrophilic groups, such as OH groups or amino groups. Some of them can be ionizable, so the ion exchange interaction take place. Then there can be hydrophobic groups in the analyte that would contribute to more hydrophobic type of interactions. And then there are neutral groups such as carbonyl or nitrile groups. The next thing that you have to find is what your sample matrix is. Is it aqueous or is it organic? And is it compatible with reverse phase ion exchange and normal phase SPE sorbents? For instance, if you have an organic extract of acidic compounds, organic extract, but you know your compounds are acidic, you can use either ion exchange or normal phase SPE. And if ion exchange is chosen, then you can use either weak ion exchanges or strong ion exchanges to retain and clean up your acidic components. So in summary, the key to successful SPE methods is to choose the appropriate SPE phase, and there are many, many phases available, to know the interactions between your analytes and the SPE phase, how the analytes behave on the sorbent, and how you can change the extraction conditions. Then you can manipulate the conditions, load, wash, and elution solvents to better clean your analytes. Keep in mind that multiple sorbent beds can be combined in a single cartridge to improve the selectivity of the cleanup method. As an example, there is a supersphere, for example, dual layer carbon NH2 cartridge, whereas contains both carbon and spherical particles of NH2 sorbent, and the carbon would remove the color, for example, from extracts, and the NH2 would remove the acidic and sugar component, so the analytes would pass through the cartridge, and that's used for pesticide analysis. Other SPE formats, cartridges is the most popular SPE format, but other SPE formats are available. The sorbent particles can be packed in different sizes of cartridges, from 1 milliliter to 60 milliliter. They can be packaged into 96 well plates. They can be bound to the discs for high throughput of the samples. For example, to load for 1 liter of water, you need a good flow through the cartridge, and you can use a disc instead. And also a more modern format, you can use a loose sorbent in a dispersive SPE tube. That's also is available nowadays. So this is a quick slide to introduce you to the idea of different bed weights and sample sizes, and the data is shown for biological samples such as plasma or serum. So the lowest bed weight in the 96 well plate can contain 15 milligrams of sorbent. then the loading volume would probably not to exceed 160 microliters in order to prevent overloading that little bed with matrix and analytes. In addition, one needs to keep in mind that the sorbent beds can retain some of the wash elution solvents. For instance, the 15 milligram bed can retain up to 30 microliters of the solvent if it remains wet after the solvent passed through. But there is a benefit of using smaller beds, and that you would require smaller elution volume if the elution is used in the SPE procedure. Now we will look at the example how wash and elution procedures are developed. We will also look at the role of pH, that pH plays even in reversed phased SPE. So our analyte in this case was tricyclic antidepressant, and the structure of the model compound amitriptyline is shown in the corner here. So if you look at the structure, it has amino group, substituted amines, and then it has a big non-polar group. That's why it says tricyclic, there are 3 cyclic rings. So you would think that there would be no issue with loading and recovering this analyte on the reversed phase C18 SPE. However, when we did the experiments and looked at the role of pH in washing and elution of the analyte, because it loads fine. But if you look at the pH, at low pH, it's because it's a base, this amino group is protonated. So at low and neutral pH, the compound has a positive charge. So its interaction with the C18 support is not as strong, and it elutes. It's starting to elute at lower percent methanol in the wash solvent. Now, at high pH, high basic pH, the analyte will be completely neutral, and you can see that it interacts with the support stronger, so it needs more methanol to start eluting. So when you pick the wash solvent, you want to have more methanol organic in your wash solvent because it would clean your sample better and elute more matrix components. So that's why you would pick probably basic pH methanol wash for this method, and then you would elute an 80% methanol. So this is kind of an unusual example to show how pH affects the wash and elution conditions for the analyte. So let's turn now for some of the supelco's SPE products. The first one that I want to show you is Supel Select. It's a hydrophilic modified styrene-based polymers that are perfect for generic SPE. The second one is hybrid SPE phospholipid that can simultaneously remove phospholipids and proteins from plasma samples and enhances MS detection by reducing ion suppression. The third one that I wanted to put in my list is SupelMIP. It's a series of molecular imprinted polymers that are highly selective for targeted analytes in difficult matrices. And they can be used to measure very, very low level of those analytes. Supel Sphere Carbon and H2 that we've seen the picture of already is a dual layer tube for pesticide residue analysis, and it's compatible with Japanese positive list system. And the last one that we're going to talk about also, Supel Q, is designed for the catches method and originally was used for multi-residue pesticide analysis. And ZSAP is our new family of sorbent when you need a more challenging matrices cleanup. So for the rest of my talk, I will focus on 3 of those products, Supel Select, Hybrid SPE, and Supel Q. So my first example will involve measuring triclosan in environmental water samples, such as creek water. What is triclosan? It's commonly known as an antibacterial agent, and it was previously found to be present in an environment. According to EPA, it should be labeled as toxic to fish and our aqueous animals, so its presence is not welcome. If you look at the structure of the triclosan, it's a pretty non-polar molecule with some polar functional groups, such as an OH group. So probably the reversed phase SP would be perfect for analysis of this compound. And we developed a method to analyze it in a small stream in the waste treatment plant, in the effluent of the waste treatment plant. So we chose to use Supel Select HLB, which is generic polymer SP sorbent that can function under reverse phase conditions, perfectly compatible with aqueous loading samples, and our samples is water. So this is a little busy slide, but I will go through it line by line so you understand how the method is developed. So we used EPA method 1692 as a base method for our SP sample, method, and that method is for measurement of pharmaceuticals in environmental water. So there's more than triclosan that's getting measured in that method. So according to that method, we should use amber glass containers, and the sample should be analyzed within 7 days. For sample preparation, we again use the EPA method to acidify sample to pH 2, and that's probably used in the method to release any analytes from binding to insoluble matter, and also to convert any acidic analytes to neutral state, to be bound to the reversed phase SP. But in our case, we didn't have an ionizable group on our analyte. And also, in the EPA method, they use EDTA, tetrasodium EDTA, to bind any interfering metal cations that can be present in environmental samples. So in our method, we use 50 milliliter, 100 milliliter loading sample volume. In the EPA method, it's 500 milliliter. So we tried to simplify the method by using less volume, and we had enough sensitivity in the end, even by using less volume. So then the SP tube is conditioned before loading the sample. So we used Supel Select HLB 60 milligram tube, and it was conditioned with methanol, distilled water, and 0.01 mole HCl. So methanol would be the strong solvent, and you want to precondition your cartridge using the strong solvent. And then in the conditioning step, you have to use the same to match. You have the last solvent used in the conditioning step has to match your sample. So our sample is in pH 2 water, so that's what we used as the last solvent in the conditioning step. Then we load the prepared sample, wash it with 10 milliliters of water. We tried to use less amount of the wash solvent, but we're not successful of doing that. We really needed the 10 milliliters to wash off the impurities. And then the cartridge was dried for 10 minutes under vacuum and eluted using 3 milliliters acetonitrile methanol mix. We also tested 6 milliliters elution as per EPA method, but we were able to elute close to 100% of our analyte. We're using 3 milliliters, so we stick with that because it was easier to evaporate. And then, as in any SP method development, you have to try to use your method with a model sample. And our model sample was plain water, and we spiked it 3,500 nanogram per liter with a triclosan, and we got 88% recovery, so we were happy about that. And we moved to our real sample, environmental sample that we collected. So if we look at the real samples, we measured triclosan in the wastewater plant effluent and in the creek water 1 mile downstream from discharge from the wastewater plant, and we did it by LCMS-MS. So we found triclosan in both samples. The amount was much higher in the wastewater plant effluent as we expected, and in creek it was diluted about 20 times, but we could still see it there. So in summary, we developed the SPE method using Supel Select SPE, and the method was successfully applied to real-world environmental samples, and the level of triclosan was found to be 120 Z in wastewater in the creek because of the dilution of the wastewater plant effluent that takes place in the creek. So our next example will include the isolation and LCMS characterization of illicit bath salts. Phenethylamine and cathinone compounds were being marketed as bath salts, and their effects on the body are similar to heroin and methamphetamine, except they're not regulated, so people can put themselves in danger, and the authorities need a method to analyze for those salts in the suspects. This set of compounds includes isobaric compounds that have the same molecular weight, and that method would require chromatographic resolution of these for positive confirmation by LCMS. So we picked Supel Select strong cation exchange sorbent because the bath salts compounds all are basic, so they will be protonated and charged at the neutral pH of the urine. And then on the SCX, they would be retained via ion exchange mechanism, and we can use high organic wash solvents to wash off all the matrix, and as a result, we can get a very clean sample. So our SPE method for bath salts, of course, included the loading sample of urine and water spiked with the bath salt mixture. Water was used as a model sample to develop the SPE method and to confirm that SPE method works. So we condition our Supel Select SCX cartridge using, again, strong wash, which is 1% formic acid in acetonitrile, followed by the water wash to match the cartridge environment to our loading sample, which is aqueous sample. Then we would load the spiked urine sample, wash with water, apply the strong organic acidic wash to wash most of the matrix components off, and apply a water wash again. Then elute the compounds using strong base inorganic to disrupt, again, those ion exchange interactions, because when you apply the strong base, you would neutralize the basic compounds and they would be eluted off the cartridge with organic solvent in the elution wash, evaporate to dryness, and then inject in LCMS. And when tested our spiked water samples, we had 76 to 90% recovery for our compound set, so we were happy again with that one. So when we use helic chromatography for looking at this set of compounds, the helic chromatography resolved all 9 compounds very nicely. You look at single peak for each compound. And also shown on this figure, the red line is when you inject the diluted spiked urine, you cannot see the very nice peaks. You can only see the matrix background. This was done by time of flight detection. And the blue line is the urine blank after Supel Select SCX cleanup, and it's just shown for the purpose that there was no interference from the blank urine with our detection. Now these are the recoveries of the bath salts using both spiked water and spiked urine samples. Using the external calibration method, recoveries were greater than 65% for all analytes, except for the first one, MDVP, which is methylene dioxypyrovalerone. But we were happy with that method. So in summary, we developed the Supel Select SCX sample preparation method, which cleaned up our matrix from urine very efficiently. We used a combination of SPE with helix separation, which is a novel approach for testing problematic bath salts. They are very polar compounds. And by utilizing an exchange mechanism, generally analytical chemists can improve the selectivity and sensitivity of difficult bioanalytical applications. And for more information, you can visit our website, which is sigmaaldrich.com/supelselect. Next, we are going to talk about hybrid SP phospholipid. These are 96 well plates and cartridges that contain zirconia-coated silica particles. They're designed for selective removal of phospholipid interferences and precipitated proteins and use a simple 2- or 3-step procedure. The benefits is that it improves LC-MS sensitivity by reducing the matrix effects, and that in turn improves the column lifetime and can speed up the HPLC separation when the gradient methods are not needed. The monitoring of phospholipid contamination is the next slide is talking about phospholipids. Phospholipids are major components of cell membranes, and you can see the graphic of the cellular membranes with compounds having polar head group and nonpolar tail that form the cell bilayer membranes. So they're present in all biological organisms, and when we do the extraction, they can be present in the extracted sample. The largest subclass of phospholipids are phosphatidylcholine, and the structure is shown on this slide. Its presence can be monitored with 2 ions in MS mass spec, which is 184 and 104 ions. And it's used as a marker for ion suppression risk for samples. It also can be a marker to show the effectiveness of sample prep technique. So why the phospholipids are the problem? This set of experiments were done by standard protein precipitation technique, and phospholipids are not removed during standard protein precipitation. So we're monitoring for 184 ion for phosphatidylcholine, and we're injecting our protein precipitated sample into the sub-2 micron column. If you notice, the run is pretty long, 20 minutes. It's because we have to apply a gradient to clean the column of the phospholipids. And even with gradient cleanup, after 20 injections, the phospholipid starts to accumulate in the column. In addition, we have increasing back pressure due to phospholipid increasing back pressure is from protein precipitation. So we need long gradients to clean the column. So what happens when we apply hybrid SP phospholipid cleanup? The phospholipids are retained on the proprietary hybrid SP zirconia-coated silica via Lewis acid, Lewis base interactions. The phosphate group of the phospholipids acts as a Lewis base and complexes with the zirconia atoms. So they are selectively retained when analytes are eluted free. The method in the 96-well format looks very simple. So we precipitate proteins in the well of the 96-well plate by using putting the sample in, such as plasma or serum, and adding 1% formic acid and acetonitrile. Then the plate is shaken to precipitate the proteins and to mix everything. Then the vacuum is applied, and the sample is drawn through the bed in the 96-well plates, where precipitated proteins are retained above the filter in the well, and then the phospholipids are retained by the hybrid SP sorbent. And after this, the resulting filtrate and eluate is free of protein and phospholipids and ready for LC-MS. So a very simple procedure. So what happens to our chromatographic run after this procedure is that we don't see a lot of phospholipids in our sample. They're 99.5% removed, and there is no change in the back pressure or the baseline of the runs. So the runs are significantly improved. So when running biological samples by HPLC, a standard protein precipitation would require cleanup gradients of the HPLC column, whereas you can improve the throughput for your samples by using hybrid SP phospholipid, because the gradients may no longer be needed. So the HPLC runs can be cut down to isocratic 2 minutes runs, and that would give you tenfold increase in sample throughput through the LC-MS instrument. This slide shows the overlay of MS analysis of methadone and metabolites extracted from rat plasma using either standard protein precipitation or using hybrid SP phospholipid plates. These plates were small volume plates, and only 20 microliters of plasma were used. And even at high concentration of all the analytes, this still shows the difference in quantitation for each peak, for each compound. Whereas protein precipitation method, the samples undergo ion suppression, and the peak has about 20 to 15% less in height than the peaks that obtained with hybrid SP small volume plate. Note that hybrid SP used actually 1/5 of the sample of the standard protein precipitation, and we still got higher peaks in this particular case. So hybrid SP technology functions using interference removal strategy, and that makes it a fast and convenient SP method. So it reduces matrix effects and can improve HPLC column lifetime and method throughput. Please note that not only it can be used to remove phospholipids from the samples, but it can also be used to concentrate phospholipids, for example, in lipidomics applications. For more information, you can find in our website, again, it's hybrid SP-phospholipid. And then we're going to talk about catches. Catches also is an SP method that uses interference removal strategy, but it's not in a cartridge, but in a dispersive format, and it was first invented by Dr. Lihote and Anastasiadis for analysis of pesticides in food, and it's a multi-residue method. It stands for quick, easy, cheap, effective, rugged, and safe, and because of its advantages, it's getting other uses except for pesticides. Other compounds are analyzed in all kinds of samples nowadays. So how does the catches method work? We weigh 10 grams homogeneous sample and add 10 milliliters of acetonitrile. Then we shake it. Then the salts are added to the sample and shaken again in centrifuge to separate the acetonitrile layer from the aqueous layer, and all the analytes of interest would end up in the acetonitrile layer. We have an option for acidic pesticides to take them out, because the next step we do cleanup with PSA and C18 sorbents. And PSA is an anion exchanger, so it can bind some of the acidic compounds. It does a good job for cleanup of the matrix, but some compounds can be lost. So if we take the aliquot then and mix it with magnesium PSA to clean it up, then shake and centrifuge again, acidify the extract, and this is for pesticide work to stabilize some of the pesticide compounds, and then we do the GCMS, OLC, MSMS analysis. So what are the choice of sorbents for the cleanup catches method? Because it is an SP seminar, it's not like really a catches seminar. So let's look at the sorbents. So the PSA, like I mentioned before, there is a PSA sorbents that would take out pigments, sugars, and acids. Then the C18 sorbents can be added to remove the fats. Then the C18 PSA mixtures can be used also. Then we can have NV-carb. The NV-carb would definitely remove some of the green pigments, the chlorophylls. And then we can use the mixtures of PSA, C18, NV-carb to basically clean up matrix really well. What I want to introduce is the family of ZSEP sorbents. Especially, they're good for fat-containing and pigmenting samples. ZSEP can be used for hydrophobic analytes, the mixture of ZSEP C18 for samples that contain less than 15% fat, and ZSEP Plus for samples that contain more than 15% fat. ZSEP family sorbents were found to be really well to remove the fat. They're probably better than C18 for more challenging matrices. And if we add it to our table, that's how they would look like. The main thing about the ZSEP sorbents that they can be used in the place of PSA C18, and they usually would do a better job. So my next example will illustrate that in the case of pesticides analysis in avocado. Avocado is a difficult matrix because it has the color, but it also contains up to 15% fat by weight. So we tested the use of ZSEP plus cleanup sorbent with avocado, and our pesticide mix included hydrophobic compounds that we thought would be tougher to analyze from the fat-containing matrix, and all our compounds are GCMS amenable. We had to change the catches extraction a little bit to include high amount of acetonitrile to increase the extraction of those hydrophobic analytes from the matrix, and we tested ZSEP plus and PSA C18 sorbents. We did this by using single quadrupole MS detector, which is a pretty challenging thing to do because there is not enough selectivity of detection when you use that detector, so you see a lot of more matrix in your samples when you use single quadrupole MS. So what we got was in the scan mode, in the GC scan mode, our ZSEP cleanup showed us less background peaks than C18 PSA cleanup, and also it removed more color from our samples. When we look at the recoveries of pesticides, we see that PSA C18 cleanup, which are blue dots, gave us less recoveries for pesticides than our ZSEP plus cleanup. And some pesticides we couldn't even see in the PSA C18 cleanup because of interference of the matrix with detection. Another thing to note is that the ZSEP plus cleanup method was more reproducible. If you look at the error bars on each point, the error bars for ZSEP cleanup are much smaller than those for PSA C18 cleanup, which in the end, better reproducibility would indicate that it's a better method. So in summary, ZSEP and ZSEP plus, that's a new family of sorbents. They're better used for removal of fatty and colored matrix components. And the thing is, you don't have to change your catches procedure to try the ZSEP sorbents. You can just put them instead of PSA C18. And they're better for hydrophobic analytes. So in order to have more information, you can go to our website /ZSEP, this one, and you can have more information on those sorbents. So in summary, we looked in this webinar at choosing the sorbents and SP hardware and how to do it more intelligently by looking at your analytes and your analytical needs. You have to pay attention to the pH of loading, washing, and diluting solvents, as it affects the recovery of the ionizable analytes, as we've seen in the multiple examples. And you have to stay informed on the new SP developments that can make sample preparation easier, faster, and more convenient. And my last slide would go through resources for SP methods that we have available on the Sigma Aldrich website. There is resources for SP in general. If you want any sample packs or products to try, there is SP samples web page that you can order them in. If you want to learn more about new technologies such as hybrid SPE or ZSEP, there is web information about those, and I will try to answer any questions that came up during the webinar. But if you have additional questions related to this presentation, you can email me at this contact email address. And thank you very much for your attention.